question 1, we've got two particles A and B having masses of m and 3m respectively. Now the particles are connected by a light inextensible string, and initially A and B are at rest on a smooth horizontal plane with the string slack, so something like this. Particle A is then projected along the plane away from B with the speed of capital U, and given that the common speed of the particles immediately after the string becomes taut is capital S, we need to find S in terms of U. So the string becomes taut. Now before the string was taut, just the moment before the string became taut, B had a speed of 0 and A had a speed of capital U, both pointing to the right. And after the string becomes taut, they are both moving to the right with a speed of capital S. Well, I'll be using the conservation of momentum. So momentum before is equal to the momentum after. Momentum is simply the product of the mass and the velocity. So 3m times 0, this is the momentum of B before the string goes taut, plus mu, this is the momentum of A, is equal to 3m times S plus ms. So we're looking at mu being equal to 4ms. Obviously the m will cancel out. We're trying to find s in terms of u, so we arrive at u over 4 being equal to s. In part B, we need to find in terms of m and capital U the magnitude of the impulse exerted on A immediately after the string becomes taut. Well, we know that the impulse is the momentum after minus the momentum before. I will be considering A. So considering A, the impulse is given by ms, which is the momentum after, minus mu, which is the momentum before. Now we have arrived at capital S being u over 4 in part A. So we're looking at mu over 4 minus mu, which simplifies to negative 3mu over 4. However, the question is asking for the magnitude of the impulse. So the magnitude of the impulse is always positive. So this is 3mu over 4 Newton seconds. In question 2, we've got two forces, P and Q, acting on a particle. Now P has a magnitude of 10 newtons and is acting due west, while Q has a magnitude of 8 newtons acting on a bearing of 330. Given that F is equal to P plus Q, we need to find the magnitude of F. Well, let's start by reminding ourselves that north is upwards, south is down, east to the right, west to the left. Now P has a magnitude of 10 newton and it's acting due west. So if I draw the north, we're going 10 newtons to the left. That's the force P. And then for the force Q, I will draw the north again. It's a magnitude of 8 newtons on a bearing of 330. So starting from the north and going clockwise, I've got 180, 270 plus an extra bit. So this is Q here. It has a magnitude of 8 newtons. The bearing is 330. I can easily resolve the 8 newtons using the fact that this angle here should be 60 degrees because all of this is 270. So 330 minus 270 is the 60 degrees here. So to the left it's 8 cos 60 and upwards it's 8 sine 60. So what I'll be doing, I'll be expressing P and Q in vector form. So P is pointing to the left, so it's negative 10, 0. While Q is pointing to the left and up, so it's negative 8 cos 60, and then 8 sine 60 is the J component. If I plug this on the calculator, they simplify to negative 4 and 4 root 3. I will start by finding the force F, defined to be the sum of P and Q. So we're looking at negative 10, 0 plus the negative 4, 4 root 3. This gives an answer of negative 14, 4 root 3. And then I will proceed in finding the magnitude of F. So the magnitude of F is found through Pythagoras. It's negative 14 squared plus the 4 root 3 raised to the power of 2 and all square rooted. Now if you plug this on the calculator, you get an answer of 2 root 61, which can also be written to 3SF as 15.6 newtons. In question 3, we're given two particles P and Q having masses of 4m and 2m respectively. These are shown in figure 1 here. Now the particles are connected by a line in extensible string, and the second line in extensible string has one end attached to Q. Now both strings are taut and vertical, and the particles are accelerating vertically downwards. Given that the tension in the string connecting the two particles is 3 mg, we need to find in terms of m and g the tension in the upper string. As always, I will start by adding all the forces acting here. So let's start with the weight of P. It's 4 mg. Now what else is P feeling? It's feeling a tension upwards. I will call this T2 because we've got two tensions acting here, because we've got two strings. We've got one string here, so I'll be calling this tension T1, and then the tension in this second string, I'll be calling it T2. Now we consider Q here, it's surely feeling its weight, but also T2, because the T2 pointing upwards, it's cancelled out by the T2 pointing downwards, and Q is also feeling a tension pointing upwards, which I'm calling T1. Now we are told that the particles are accelerating vertically downwards, so I've got acceleration pointing downwards, and we are given that the tension in the string connecting the two particles, so T2 here, is equal to 3 mg. I will be considering P, then considering Q, trying to find in terms of m and g the tension in the upper string. So starting with P, if we consider P, we know that P is accelerating downwards. So forces acting downwards, that's 4 mg, minus forces acting upwards, that's T2, is equal to 4 ma. That's mass times acceleration. And then considering Q, now Q is also accelerating downwards, so the forces acting downwards minus the forces acting upwards will be mass times acceleration. So we're looking at 2 mg plus T2 minus the T1 is equal to 2 ma. I will proceed by substituting into the first equation for P, T2 with 3 mg. So we're looking at 4 mg minus 3 mg being equal to 4 ma, taking me to mg being equal to 4 ma. Obviously the m's will cancel out, and we arrive at g over 4 being equal to a, the acceleration. And then going to the second equation here, I'll be substituting T2 and the acceleration a. So we're looking at 2 mg plus the tension 2, which is 3 mg minus T1 being equal to 2m times the acceleration of g over 4. This takes me to 5 mg minus T1 being equal to mg over 2, and therefore 9 mg over 2 is the tension 1. It's the tension in the upper string. In question 4, we're given a non-uniform rod AB with a length of 6.5 meters and a mass of 1.2 kilograms. Now the center of mass of the rod is 3 meters from A. It is resting on a horizontal step and overhanging the end of the step C by 1.5 meters as shown here in figure 2. Now the rod is perpendicular to the edge of the step. A particle of mass 4 kilograms is placed on the rod at B, and another particle with a mass of capital M kilograms is placed at D, where AD is 0.5 meters. Now the rod remains in equilibrium in a horizontal position, and we need to determine the smallest possible value of M. Let's start by adding everything that is involved here. We start with the weight of 1.2 g. This at a distance of 3 meters from A. We then proceed with the particle placed at B having a mass of 4 kilograms, so 4g acting on B. And then we've got D, where AD is 0.5 meters, with a particle with a mass of capital M. So D is here. We've got mg acting on D. The distance AD is 0.5 meters. Now the rod remains in equilibrium in a horizontal position, and to determine the smallest possible value of M, we need to consider the scenario where this rod is about to tilt about C. So if I consider C here to be the point of interest, the distance of the center of mass here up to C, it's gonna be 2 meters, because this is 3 meters, this is 1.5 meters. So 3 plus 1.5 is 4.5. If I deduct this from 6.5, I get the 2 meters. And then the distance of D from C, this distance here is 4.5 meters. And I can proceed in taking moments about C. So clockwise moments, it's the B acting at a distance of 1.5 meters. So the clockwise moment is 1.5 times the 4G. And the anti-clockwise moment, it's gonna be the D, which is acting at a distance of 4.5 meters. So 4.5 times capital mg plus the 2 times the 1.2g. So we're looking at 6g being equal to 4.5 mg plus 2.4g, taking us to 3.6g being equal to 4.5 capital mg. Obviously the g's will cancel out. If I divide both sides by 4.5, we arrive at 0.8 being the value of capital M. The particle at B and the particle at D are now removed, and a new particle is placed on the rod at the point E, where EB is 0.9 meters. Now the rod remains in equilibrium in a horizontal position, but is on the point of tilting about C, and we need to determine the magnitude of the force acting on the rod at C. So this is the diagram we had up to now. So the center of mass is 3 meters from A, the weight is 1.2 g. Now we've got this point E, so we've got a particle placed at E. We don't know the mass of it, so I'm just gonna call the weight mg. Now EB is 0.9 meters, and now I will add a reaction at C because we are on the point of tilting about C. So we've got the reaction at C. The point of interest now, it's point E, and I will be considering the distance of each force from E here. So we start with the 0.6 meters. That's the distance between C and E. All of this was 1.5. This is 0.9, so the difference is the 0.6. And then the distance between the center of mass and E is 2.6 meters. We simply did 6.5 minus the 3 minus the 0.9. So we can proceed by taking moments about E. This will eliminate the presence of M, which is unknown, into our moments equation, and will allow us to recover the value of the reaction at C. So considering moments about E, we've got RC here acting in a clockwise fashion. So we're looking at 0.6 RC being equal to the 2.6 times 1.2 G. So RC is equal to 2.6 times 1.2 G, and all divided by 0.6. Now if I proceed by substituting G to be 9.8 and plugging this on the calculator, we get RC to be 50.96. But since we have used G to be 9.8, we need to give our answer to 2 or 3 significant figures. So RC turns out to be 51.0 newtons. In question 5, a parachute is used to deliver a box of supplies. The parachute is attached to the box. Now the parachute and the box are dropped from rest from a helicopter that is hovering at a height of 520 meters above the ground. The parachute and the box fall vertically and freely under gravity for 5 seconds, and then the parachute opens. From the instant the parachute opens, it provides a resistance to motion of magnitude 3,200 newtons, and the parachute and the box continue to fall vertically downwards after the parachute opens. We are modeling the parachute and the box throughout the motion as a particle capital P of mass 250 kilograms, and in part A we need to find the distance fallen by P in the first 5 seconds. So I'll be using Suvad equations here. During the first 5 seconds we are falling freely under gravity, so I'll be using S is ut plus a half at squared. The initial velocity was 0, the time is given to be 5, and the acceleration is 9.8. It's simply g. So we're looking at S being 0 plus the half times the 9.8 times the 5 squared. Now if we plug this on the calculator, we'll get an answer of 122.5, and therefore we conclude that the distance fallen is 123 meters. Be careful here. since we have used G to be 9.8, we need to reporting our final answer here to 2 or 3 significant figures to claim both marks. In part B, we need to find the speed with which P lands on the ground. So I will start by finding the speed when the parachute opens. I'll be using V is U plus AT. We know that we started off with an initial velocity of 0 and we are experiencing an acceleration equal to G. So V is equal to 0 plus 9.8 times 5. This gives an answer of 49 meters per second, which is the speed of P when the parachute opens. And I will proceed by drawing a quick diagram to find the acceleration when the parachute opens. So this is the particle P accelerating downwards. We've got the weight to be 250 G, but we've got the resistive force of magnitude 3,200 newtons. So considering the fact that we're accelerating downwards, I'll be doing forces downwards of 250 G minus forces upwards, which is 3,200, being equal to mass of 250 times acceleration. So we've got 250 times the 9.8 minus the 3,200 being equal to 250A, and therefore we've got negative 750 being equal to 250A, which means that the acceleration was equal to negative 3 when the parachute opens, which means I can proceed with Suvat equations for the part of the journey when the parachute is open, and therefore we're experiencing now a constant deceleration of 3, and this will help us find the speed when P lands on the ground. I'll be using V squared is U squared plus 2AS. We're trying to find V, so V squared will be the 49 squared because the initial velocity for the part of the journey when the parachute opens is 49 meters per second. It's the final velocity up to the moment that we are falling with gravity, the moment the parachute opens, and then we've got plus 2AS, so plus 2 times the negative 3. We know we had to cover a total distance of 520, and we have already covered the 122.5 meters that was found in part A. This leads to V squared being equal to 16, and therefore V, the speed with which P lands on the ground, is 4 meters per second. In part C, we need to find the total time from the instant when P is dropped from the helicopter to the instant when P lands on the ground. So I'll be using V is U plus AT to find the time from the moment the parachute opens up to the moment that P lands on the ground. So we had the final velocity to be 4, which is equal to the initial velocity of 49 plus the acceleration of negative 3 times t. So 4 is 49 minus 3t, taking us to 3t being 45, and therefore t is 15. Now this is the time from the moment the parachute opens up to the moment the P lands on the ground. We also had 5 seconds falling under gravity, and therefore the total time taken is 5 plus 15, which gives an answer of 20 seconds for the total time of flight. In part D, we need to sketch a speed time graph for the motion of P from the instant when P is dropped from the helicopter to the instant when P lands on the ground. So this is the speed time graph. We know that we set off with an initial speed of 0, attaining a speed of 49 meters per second after 5 seconds, and then we're experiencing constant deceleration of 3, so a straight line going downhill, something like that, attaining a final speed of 4 meters per second after 20 seconds, which is the moment when P lands on the ground. In question 6, we've got a box of mass m lying on a rough horizontal plane. Now the box is pulled along the plane in a straight line at constant speed by a light rope. This rope is inclined at an angle theta to the plane as shown in the figure here. Now the coefficient of friction between the box and the plane is 1/3. We are modeling the box as a particle, and we are told that tan theta is 3/4, and we need to find in terms of m and g the tension in the rope. As always, I will start by adding all the forces acting here. We've got the weight, which is mg, and obviously there's a reaction because there is the box touching, sitting on the ground here. Now we've got the tension in the rope, and we've got friction towards the left because we are pulling the box towards the right, so friction is opposing motion. And I will proceed by resolving the tension here, which is acting at an angle theta above the horizontal. The horizontal component is t cos theta, and the vertical component is t sine theta. Now we are told that the box is pulled along the plane at constant speed. This means that the friction here has attained its maximum value. Let's start by using the fact that tan theta is 3/4. I will draw a right angle triangle here. So there it is. Tan theta is opposite over adjacent. So it's a 3-4-5 triangle. So we're looking at sine theta being equal to 3/5 and cos theta being equal to 4/5. I will then consider the vertical forces. So the forces acting upwards are equal to the forces acting downwards. This means that we're looking at r plus t sine theta being equal to mg. And then since we're moving at a constant speed, there is no resultant force along the horizontal, which means forces acting to the right is equal to forces acting to the left. So we're looking at t cos theta being equal to f. And we have said that f has attained the maximum value, so f is equal to f max, which is equal to mu r. I will proceed with the fact that sine theta here is 3/5, so we're looking at r plus 3t over 5 being equal to mg, and we also have that 4t over 5 is equal to f. I will be substituting f and r into the equation here. So we've got that capital R is equal to mg minus 3t over 5, and therefore we're looking at f, which is 4t over 5, being equal to mu, which is 1/3, times the r, which is mg minus 3t over 5. I will proceed by expanding. We get 4t over 5 being equal to mg over 3 minus t over 5. I will be collecting the t's on the left hand side, so we're looking at capital T being equal to mg over 3 newtons. The rope is now removed and the box is placed at rest on the plane. The box is then projected horizontally along the plane with speed u, and we're again modeling the box as a particle. Now when the box has moved the distance d along the plane, the speed of the box is a half u, and we need to find d in terms of u and g. So let's draw a diagram here. We've got the box sitting on the plane. It's projected with speed u. So when it has moved the distance d, it has a speed of a half u. There it is. So we've got acceleration to the right because the direction of motion is towards the right. We have covered the distance of d. Let's add the forces acting on the box. We surely have the weight. We've got a reaction and we've got friction opposing motion. So let's start with the first fact that the friction F has attained its maximum value because the box is moving. It's F max, which is equal to mu R. We know that mu is a third and R is mg, so we're looking at F being equal to a third mg. And then if we consider the box here, the box is moving to the right, so we'll be doing forces to the right, which is nothing, minus forces to the left, which is F, is mass times acceleration. So we're looking at 0 minus F is equal to ma, and therefore we're looking at minus 1/3 mg being equal to ma. Obviously the m's will cancel out, so the acceleration is negative 1/3g. We are not surprised that we get the negative answer for the acceleration because the speed of the box is decreasing. It was u, and then at the end it's a half u. So I can proceed with Suvat equations. So I'll be using v squared is u squared plus 2as. The final velocity is a half u, so a half u all squared is equal to the initial velocity, which is u squared, plus 2 times the acceleration of minus 1/3g times the distance covered, which is d. So we're looking at u squared over 4 being equal to u squared minus 2/3gd. So 2/3g times d is equal to 3u squared over 4. Remember, we're trying to make D the subject of the formula, so I will cross multiply here. So this leads to 8GD being equal to 9U squared, which means that D is equal to 9U squared over 8G. In question 7, we're looking at two speedboats A and B, each moving with constant velocity. Now the velocity of A is 40 kilometers per hour due east, while the velocity of B is 20 kilometers per hour on a bearing of an angle alpha, where alpha is an acute angle, it's between 0 and 90 degrees, satisfying that tan alpha is 4/3. Now we are modeling both boats as particles, and we need to find, in terms of I and J, the velocity of B in kilometers per hour. So let's start by drawing the bearing here. It's 20 kilometers per hour on a bearing of an angle alpha. I will start by drawing the north. We turn clockwise through an angle alpha. We're traveling at 20 kilometers per hour. So I will resolve this into a horizontal and a vertical component. So the horizontal component is 20 sine alpha and the vertical is 20 cos alpha. And using the fact that tan alpha is 4/3, we can draw a right angle triangle. Tangent is opposite over adjacent, so we're looking at a 3, 4, 5 triangle, and therefore we've got that sine of alpha is 4/5 and cos of alpha is 3/5. This means we can proceed for the velocity of the boat B, which is the I component, which is 20 sine alpha I, plus the J component, which is 20 cos alpha J. Now we'll be replacing sine alpha with 4/5, so we're looking at 20 times 4/5 I plus 20 cos alpha, and cos alpha is 3/5, so 20 times 3/5 J, which simplifies to 16 I plus 12 J, and this is kilometers per hour for the velocity of the boat B. Now at noon, the position vector of A is 20j kilometers and the position vector of B is 10I plus 5j kilometers, and then t hours after noon, the position vector of A is r kilometers, where r is 20j plus 40ti, and the position vector of B is s kilometers, and we need to find an expression for s in terms of t, I, and j. So the position vector of B, which is s, is given by the initial position vector, which I will call r naught, plus u times t, and we've got no acceleration, so it's simply the initial position vector plus the velocity vector times the time. Well, we are given the initial position vector is 10I plus 5j, so we're looking at 10I plus 5j plus the velocity we found in part A, which is 16I plus 12j, and that's multiplied by t. I will be grouping together the i's and then the j's, so we're looking at 10 plus 16t I, and then we've got 5 plus 12t j, and this is meters. In part C, we need to show that at time t hours after noon, the vector AB is given here by this expression in terms of t, I, and j. So we know that the vector AB is given by the position vector of B minus the position vector of A. Now the position vector of B is what we found in part B, so we're looking at 10 plus 16t I plus the 5 plus 12t j. This is the position vector of point B, and then the position vector of A is simply the 40t I plus the 20j. I simply need to collect the i's and then the j's together. So we're looking at 10 plus 16t minus 40t. This is the I component of the vector, plus 5 plus 12t minus 20, and that is the j component. Let's simplify things. We are looking at 10 minus 24t I, and then we've got 12t minus 15. That's the j component as required. In part D, we need to show that the two boats will never collide, and for the boats to collide, this simply means that the vector AB is exactly 0, and this means that this component here should be 0 and the j component should be 0 as well. So we've got 10 minus 24t is equal to 0, and at the same time we need 12t minus 15 to be equal to 0. So we're looking at 10 is 24t, and if I divide both sides by 24, I get an answer for t of 0.4, and we also have 12t being equal to 15, and if I divide both sides by 12, we arrive at t being 1.25. Well, we can easily see that the two values do not agree, and since we've got different values of t, this simply means that the two boats will never collide. In part E, we need to find the distance between the boats when the bearing of B from A is 225 degrees. Once more, let's start by drawing this bearing. We've got the north. We're looking at the north, turning clockwise through 225 degrees. The bearing of B from A means we are standing at A, trying to go towards B. Obviously, the acute angle with the horizontal here, it's 45 degrees. Because all of this is 270, if I deduct the 225, I get 45 degrees. And if I close the triangle here, we are looking at an isosceles right angle triangle, which means that the vector AB must be parallel to the vector -1 because we go to the left, and -1 because we go downwards. So let's see, we had AB being the vector 10 minus 24t, that was the I component, and 12t minus 15 was the j component, and this is parallel to the vector -1, -1. So we've got 10 minus 24t over the 12t minus 15 being equal to -1 over -1. Obviously, the right hand side is simply 1, so if I cross multiply, we're looking at 10 minus 24t being equal to 12t minus 15, which leads to 25 being equal to 36t, and therefore 25 over 36 is the value of t, at which point the bearing of B from A is 225 degrees. I will then proceed by substituting this value into the vector AB. So we're looking at the vector AB being equal to 10 minus 24 times the 25 over 36. This will give me the I component. And then we've got 12 times 25 over 36 minus 15, which will give me the j component. Well, this simplifies to -20 over 3i, and we've got -20 over 3j. Remember, we are asked to find the distance. The distance is the magnitude of this vector. So the magnitude of AB here is found through Pythagoras. We've got -20 over 3 raised to the power of 2 plus -20 over 3 to the power of 2, and all under a square root. If you plug this on the calculator, you get 20 root 2 over 3, which correct to three significant figures is 9.43 kilometers. In question 8, we've got one end of a light extensible string attached to a particle A of mass 2m. The other end of the string is attached to a particle B of mass 3m. Now A is held at rest on a rough plane which is inclined to horizontal ground at an angle alpha, satisfying that tan alpha is 5/12. The string passes over a small smooth pulley P fixed at the top of the plane, and B is hanging vertically below P with the string taut at a height of h above ground as shown in the figure here. Now the part of the string between A and P lies along a line of greatest slope of the plane, and the two particles, the string and the pulley, all lie in the same vertical plane. We are told that the coefficient of friction between A and the plane is 11/36, and particle A is released from rest and begins to move up the plane. We need to show that the frictional force acting on A as it moves up the plane is 22 mg/39. I will start by adding all the forces acting here. So considering B, we've got the weight of 3 mg acting downwards and tension pointing upwards. We know that B is accelerating downwards, so I'm putting acceleration facing the downwards direction. And considering A, we've got the tension along the string, we've got the weight of 2 mg, which I can resolve into 2 mg cos alpha perpendicular to the plane and 2 mg sine alpha along the plane. we've got the reaction capital R, and since the particle A will be ascending up the plane, we've got friction opposing motion, so friction is acting down the plane, and we've said that A is accelerating up the plane with exactly the same acceleration as the one that B is descending downwards. Now we are told that tan alpha is 5/12, so if I draw this right angle triangle here, it's opposite over adjacent. It's a 5, 12, 13 triangle, which means that sine of alpha is 5/13 and cos of alpha is 12/13. And considering the forces acting perpendicular to the plane, we've got that R is equal to 2mg cos alpha, and using the fact that cos alpha is 12/13, we're looking at R is 2mg times 12/13, and therefore R is 24mg/13. I can then proceed with the fact that the friction is attaining its maximum value, so F is F max, it's equal to mu R. So we are told that the mu is 11/36. The reaction R, we found this to be 24mg/13. So if we do this calculation, we arrive at capital F is 22mg/39 as required. In part B, we need to write down an equation of motion for B. So considering B is accelerating downwards, so forces acting downwards minus forces acting upwards is mass times acceleration. So we are looking at 3mg minus t is equal to 3ma. In part C, we need to show that the acceleration of A immediately after its release is a third g. So going back to the diagram here, considering A is accelerating up the plane, so forces acting up the plane minus forces acting down the plane will give me the resultant. So if we start by considering A here, we've got that capital T minus the friction plus the component of the weight, so 2mg sine alpha is equal to the mass of 2m times the acceleration. Now we're looking at capital T minus the frictional force, which we found to be 22mg/39 plus 2mg times the sine of alpha, which is 5/13, and all of this is equal to 2ma. So we're looking at capital T minus 22mg/39 plus the 10mg/13. These two are in brackets, is equal to 2ma, and therefore we've got that capital T minus 4mg/3 is equal to 2ma. I will then proceed by recalling the equation of motion for B. So we have 3mg minus t is 3ma, so I can add the two equations up. So 3mg plus the negative 4mg/3 should be equal to 5ma. So 3mg minus 4mg/3 is equal to 5ma. So we're looking at 5mg/3 being equal to 5ma. Now obviously the 5's will cancel out, the m's will cancel out, so all in all we are left with a third g being equal to a as required. Now in the subsequent motion, A comes to rest before reaching the pulley, and we need to find in terms of h the total distance traveled by A from when it was released from rest to when it first comes to rest again. So this was the diagram we had originally. Now as A ascends on the plane, we've got a moment at which the string goes slack. It has covered the distance of h up to this moment because this is the moment that B hits the ground here, and then we've got the string going slack and ascends a further distance of d. It comes momentarily at rest at this point here, and we need essentially to find the sum of h and d. So I will start by finding the speed of A the moment the string goes slack. I'll be using v squared is u squared plus 2as. So v squared is the initial velocity of 0 squared plus 2 times the acceleration, which we found to be a third g, times the distance covered, which is h. So we are looking at v squared being equal to 2gh over 3, and therefore v is the square root of 2gh over 3. This is the speed of A the moment the string goes slack, and I can therefore proceed in finding the distance that A covers while the string is slack. This is the distance d here on the diagram. Now, the moment the string goes slack, there is no longer tension in the string, so we've got a new acceleration. So to find the acceleration for this part of the journey, I just need to consider that there is no force acting upwards. It's just the friction and the component of the weight acting down the plane. So we've got 0 minus the F plus 2mg sine alpha is equal to 2ma. So we're looking at minus 22 mg over 39. The friction is still at its maximum value, it's F max, minus the 2 mg times sine alpha, which is 5 over 13, being equal to 2 ma. This leads to negative 22 mg over 39 minus 10 mg over 13 being equal to 2 ma, and therefore we're looking at minus 4 mg over 3 being equal to 2 ma. The m is common to both sides. I will cancel it out. I will divide both sides by 2, and we arrive at a negative 2g over 3 to be the acceleration while the string is slack. We can therefore use v squared is u squared plus 2as again, and this time v is 0 because we're looking at the moment when a comes to rest. So we're looking at 0 squared being equal to u squared. Now the initial velocity for the leg of the journey when the string goes slack is simply the final velocity we found here. So we're looking at 2gh over 3 square rooted raised to the power of 2 plus 2 times the acceleration of negative 2g over 3 times the distance covered, which we have called this to be d. So we're looking at 0 being equal to 2gh over 3 minus 4gd over 3. So we've got 4gd over 3 being equal to 2gh over 3. Obviously, the 3's will cancel out, the g's will also cancel out, and therefore we arrive at d being equal to h over 2. And we can therefore proceed in finding the total distance, which is simply h plus d. So we're looking at h plus h over 2, which is 3h over 2.